again, and welcome to Environmental Geology. This is going to be Lecture 7 of the series. And as a reminder about Lecture 7, the midterm or the second exam will be based on Chapters 5, 6, and 7. So be prepared to get ready for that. The timers will kick in and check the schedule to make sure you're all set. The topic for Lecture 7 will be on mass movement, and you should focus on Chapter 8 in Abbott. And make sure you cover that material along with the study guide, pre-test terminology guide. Now, mass movement is kind of just what it implies, that a large mass or amount of the surface of the Earth usually is going to move in some fashion. Sometimes it's very, very slow, and sometimes it's going to be really fast. And so what we're going to do today is look at all the different kind of styles of mass movement, talk about some of the triggering mechanisms and some of the variables that are involved with that, and look at a few examples from around the country and the world and see that you can get a better understanding of what happens to some of this kind of mass movement. In the beginning, I want to look at a few examples of some types of mass movement. Here we have the typical California scene, where in the springtime with a lot of rains and sometimes the thawing of any frozen ground, it breaks loose and all of a sudden the side of a hill caves in. And in the case of this shot, the unfortunate home is mostly mashed up at the bottom of the hill, and the other houses still hanging there by a thread are next. And so it's a pretty common thing of seeing this type of stuff all over the country. You may be out in the middle of nowhere sometimes. Here we have a spot in Utah, Zion National Park, where part of the highway gave way, and of course that, a lot of traffic may go on there. It's narrow, so it's going to take a lot of time to fix that, and sometimes the road's completely shut off, like here in Aspen, Colorado. I'm not sure if you can catch the little arrows pointing to a car that missed stopping down in the bottom, and the guardrail's kind of bent, and so a situation like this can take quite a while to repair that hazard. Railroad system in Germany. It doesn't have to be a highway, anywhere where the earth can move in some fashion and cause havoc. This one that occurred near Thistle, Utah. It's a really large mudslide that took place in the spring sometime back, and the whole side of the mountain up here on the top area gave way and slid down into this valley and blocked off a small river that was flowing through. And right underneath the water, behind the bottom of this lake, is where the little town of Thistle, Utah was. So everybody was evacuated. Nobody got hurt, but it caused a lot of problem on this main highway. In the bottom left, you can see a brand new highway that was cut through the mountain. They also started a whole new railroad system, tunnel that used to go around on the valley. They cut it through the mountain, right down here in the bottom where the cursor is, where the new tunnel comes out, and they had to move a lot of stuff. And so it took almost a year to fix this, and it still has its problems every spring. There's still some material that loosens and falls and slides, and so the people who lived in this region, who commuted to Salt Lake City, had to drive way out of their way. Hours of extra driving each day just to make it to work. So it was a very big inconvenience when something like that happened. So whether it's activity where we can see it and it involves us, sometimes these things may be in the middle of nowhere, and often you don't see it. You don't even hear it. On the left, we've got an example of a large mass of rock that just slid down and fell through the air and landed at the bottom of a cliff in the Navajo sandstone out in one of the monuments in Utah. On the right, again, a large mountain mass, probably overburdened with water, slid down, maybe triggered by vibrations from an earthquake, slid down, blocked up a river, and created a lake, now called Earthquake Lake because of the movement. Plan on living in Florida. Florida has a lot of limestone underneath it, and it rains a lot. It's very wet. And so through a lot of chemical weathering, we'll see later on that sometimes you can dissolve all that limestone in the subsurface, and the surface simply collapses or sinks inward. Again, we've got a few vehicles in this image that have fallen in and become kind of victims to this sinking ground. Sometimes this happens pretty fast. Right here in Kansas, we've had the same thing, where the railroad track that went over it had to be rerouted as something occurred here. We're going to talk about some of the reasons why we have the Kansas type sinkhole. A long time ago in the Panama Canal in the construction, it's a very weathered zone, warm, a lot of rain. You dig in a deep canal, you're undercutting the slopes, and all of a sudden huge mudslides and landslides would come blowing down into the construction sites and hold it up. Had a lot of problems with that. Well, we still do. 1986 had some recent slides that came down into the canal. Well, you've got to get the equipment in there and dredge it out and keep that going. It interferes, of course, with commerce to keep moving the ships through the canal. So I want to look at now a list, some names of examples of types of mass movement, kind of categorize them in a general sense. Okay, so you should write down the title of this list, the types of mass movement. And then I'll point out some of the examples in the kind of the cartoons on the right. And the first type, of course, is a fall. And what a fall simply means is that the material that breaks loose from a cliff, like we see in the top left part of the cartoon, is at whatever size it is, it simply free falls through the air and ends up as a pile, what we call a talus pile, at the bottom of that cliff. So it's pretty much free falling through the air. Flows are kind of what the word implies, water flows. So usually there's a lot of kind of water-like movement. The material, whether it's soil, vegetation, unconsolidated material that kind of moves like a liquid, like a fluid, flows down the hillside. Pretty much a lot of internal turbulence to it. So we would classify things like that as flows. Mud flows, earth flows. Slides. The main kind of slide, of course, is simply for the massive material to slide down some type of planar surface. Generally, we say it's a flat plane. It has a basal slip. It will slide down the hill like we see on the bottom left-hand part of the cartoon. And again, it could be an earth slide, a rock slide. And of course, with the exception of the fall, which free falls, and that's under the force of gravity, and can pick up a certain velocity coming through the air of acceleration, a lot of the speed at which these different types of flows and slides go depends on a number of things, like the steepness of the slope or how much water is involved and that type of stuff. Now, subsides, I use the word subsides here because that's the one they use in your textbook. And the example is over in the bottom right-hand corner of the cartoon, where the surface of the earth vertically drops downwards, subsides or sinks. We'll see another term for this same thing called subsidence. Subsidence and subside are the same thing. Numerous examples of that right here, again in Kansas. Now, kind of a specialized case of a slide. Kind of a specialized case of a slide is referred to as a slump. And I'll wait till we get to some better images of what slumps are to help you describe and delineate the differences between a more typical slide and what we call and define a slump. Creep is a special case of downward movement of the surface of the earth. And again, I'll wait till we get some images of what goes on in the mechanics behind what we call creep. Okay? So falls, flows, slides, subsidence or subsides, and some specialized cases, slumps and creep. And one last one I'm throwing at you because of the kind of character or more of a geographic place where this type of movement is similar to creep, but it's in a certain geographic region in the world, and we'll get to that as well. Now, there are other subtle styles. If you're in engineering classes, we get into this a little bit more, but this is kind of the main category of all the types of mass movement that we're going to look at in this class. Now, obviously, the number one force is helping things move downward. It's going to be the force of gravity. All right? The force of gravity. And you have a nice little kind of cross-section picture in your textbook where they look at some vector forces of what's going to involve how that might slide downhill. And they bring into some kind of trigonometric approaches to this. We're not going to do any trigonometry in here and calculate normal vectors and and slip vectors with that in mind. Okay, we're just kind of the idea that the force of gravity is going to pull things downhill, and it will help with how fast that moves downhill. All right, now what's going to determine how stable a slope is, such that once it becomes to a point of instability, it begins to move? All right, so let's go through a list of slope stability factors with this slide. The composition of the material at the surface of the earth and the structure of the slope materials come into play. Now, composition refers to what kind of rock type it might be, igneous, sedimentary, or metamorphic. It could be unconsolidated material like sand, silt, clay, different styles that are unconsolidated. They're not cemented into a particular type of rock. The structure of the slope material, we could start out with some simplicity like how fractured is it? How weak is it through physical and chemical weathering? Another thing about the structure of a material could be, how steep is the slope? Or what's the orientation of the layers of the rock on that slope? Are they tilted into the slope? Are they tilted with the slope? All that makes a difference. And engineers need to evaluate that as they look at particular slopes and attempt to mitigate them to protect us. Now we're going to see that water plays a very important role in mass movement. The amount of water, the more water you have, the more trouble we're going to have. The more water you have, the more trouble, the more unstable the slope becomes. Now certainly, again, that angle of the slope, the steeper the slope, usually the more unstable the slope will be when you think about gravitational forces involved. If you've ever driven along a particular construction site on a highway somewhere, you might see that they're attempting to plant various types of vegetation along that slope to help kind of bind it and hold it together, prevent and slow down erosion of the slope. So the presence or absence of vegetation, the more vegetation you tend to have, the more stable the slope will be. So if you have a fire and you get rid of that vegetation, you're going to make that slope more prone to becoming unstable and therefore have mass movement take place. All right, I want to look at some triggering mechanisms. What could help? Say a slope begins to get towards being unstable for whatever reason we went through in that last list. Sometimes all it takes is a little extra oomph to shove it over the edge and make it happen. So this is a list of triggering mechanisms. And one way to do it is simply overload the slope. If you go in and you, through construction, add weight to the hillside, in whatever way, you're overloading that, and that's going to make that substrate, the base material, become unstable and have the potential to move. Or you can undercut a slope. By undercutting a slope, you oversteepen the slope, and by oversteepening the slope, of course, you weaken it. It has the greater chance of moving. Now, vibrations certainly can help shove it over the edge. Now, probably the biggest type of vibration that's involved in some of the bigger movements are natural earthquakes. You get a pretty big earthquake with a good vibration of the ground and you have an unstable slope, it's going to go. It usually will begin to move. And out in California, we see this happen a lot. Now, we may have some bombs that are detonated, whether they're in a mining situation or whether it's in a war situation. Again, if there's enough vibration with that particular explosion, it's going to help cause the slope to move. Even sonic booms. Continual sonic booms under the SST, they're always worried about some of the effects besides noise pollution and whatever, that in some areas you get that constant booming with every takeoff over a certain region. It's enough to just have a little jar and keep jiggling it, keep moving it. Eventually it could cause it to move. And now we can get back to water again. Add water. Water's weight. You get a lot of heavy rains in a region and the ground can really soak up that water. The water percolates into the fractures and gets into the pore spaces. You're adding weight again. You're overloading by simply adding that water. So what is it about water? Let's kind of look and list a few things about the role of water here. And as I said, by putting more water in there, you add weight. But water can also do other things. Water can physically erode and physically weaken an area, especially if it freezes and it expands and pushes outward, open cracks even more so, or through chemical erosion to turn certain minerals into softer minerals, which thus are weaker, making the slope more unstable. And of course, we know that water acts as a lubricant, can help make it slip, and it has a buoyancy type of character to reduce the weight of the rock on top of something to help it be less. So essentially, I guess we could say water's bad. We don't want to have water around. So in slopes, we want to do something about it. We'll look at that later on with some of the mitigation stuff. All right, let's take a look at some of these types then, some different types of the mass movement. This cartoon from your text is trying to show you something about the process of creep. And one thing you need to remember about creep, it's a very slow process. And you can even, you tend to see it a lot in the cartoon. We can see the fences are tilted over here, the telephone or power lines are tilted over. You might see trees when you look at them, they all have a curved basal trunk. Remember, trees want to grow up towards the sunlight. And so as they grow and the hill bends and slides over down the hill and slowly creeps down that slope, the tree is going to still want to curl back up vertically towards the sunlight, and you get these curved trunks on the bottom. In cross-section view, the layers, the actual layers of the rocks, the layers of the soil will show a continuous kind of uniform curvature or bending down the hill. Now, creep is something that happens everywhere, pretty much, across the whole globe. And even though it's very, very slow, it's extremely damaging. If we look at the number one cost of the different types of mass movement that we have to fix, and, a big landslide, yeah, it is dynamic, you see it, tends to get fixed rather quick, but this just continually goes on and on and on, and it's everywhere. And so the number one cost you should remember is that creep costs the most to repair over the long run. Now, kind of what's happening is that in the upper zone of the earth here, in the upper several feet or so, what tends to happen is that the clay minerals that are there will tend to expand and contract, enlarge and shrink, swell and shrink, back and forth. That's kind of a movement. So I want to kind of look at here's some examples of how the rocks are bending down the hill on the left-hand side here. Here you can see these trees, the trunks are sliding and curving downhill. Okay? I think I have another shot here about how creep kind of works. We want to get something that causes these things to expand and contract as it moves and migrates in a slow fashion, kind of like a super slow flow. Another way to look at it. And so one thing that could happen, if you can have freeze and thaw will cause expansion and contractions. Wet and dry scenarios will cause expansion and contraction, as well as kind of heat and cooling. A lot of times in deserts it gets super hot, at night it gets very cool. And that continual shifting of those variables causes the material to expand and contract, and that's simply weakening it. And it slowly busts apart, moves its way downhill in a very slow type of fashion. So try to remember these three kind of variables, types of conditions. Freeze, thaw, wet, dry, or hot, cold, or in this case, the heat and cooling effect. Here's kind of a photograph from an airplane in California, some, creep. It's like the hillside is just slowly flowing down, slipping down that hillside or that slope in this case. So up here on the right, you can see where it's breaking loose, and it's moving down towards the left and buckling and kind of folding as it slides into this little confined valley. Now we can see this even here in Kansas along the Interstate 70s. You drive around Lake Wilson and eastward. Just take a look at some of the slopes and you'll see where that stuff is slowly kind of moving downhill. That's creep. Look for some of the other evidences too, sometimes the tilted telephone poles or the bent tree trunks. Here's this special case of a type of kind of slide. One of the key things I want you to look at in this picture from your book, and it's what we define as slumping, a slumping process. And for all our purposes in this class, what I want you to remember about this specialized case that we call slump is that the rupture surface, the slippage surface that it's occurring on, underground, is beneath it, is that it's curved. So please associate the word curved with slump in this case, kind of a specialized thing. And it can involve rocks. It often involves unconsolidated materials. But in engineering, we can get into all kinds of definitions of the parts of this, from the crown down to the toe, so to speak, and what it looks like. But for us in here, I'm going to show you some examples of some of these slumps. But I definitely want you to remember that it moves along a curved basal surface. Now, our geology students out here at Fort Hays State have a project when they're seniors to go out along the Saline River. And we have some of the most dynamic structural geology out there along that river, these huge slumps that take place. On the right is a cartoon that I drew, okay? And what makes up the cliffs or the escarpments along the valley are these more resistant limestones, the Fort Hays limestone. And these black lines represent big vertical fractures or joints that are in there. The kind of stippled area, thinner area, is the Codell sandstone. It's kind of crumbly and soft. And underneath that, the white area is Blue Hill shale. And this shale is made up of a lot of clays, and it's kind of slippery. And so what's going on is that out here towards the valley is air. This is down into the valley. And so there's no lateral support, and this block right here wants to move downward, as I've shown by this bigger, kind of fatter arrow. It wants to move downward. All right? Well, as it does, that gravitational push, it starts to slide down right along the joints. So in the beginning, the amount of drop is equal to how thick the limestone is. But once that tip here in the corner gets down to a point, then it really slides on that major curved surface or slumps in that direction. And you can see that these rock layers have changed their orientation. Here at the kind of the toe, you got a lot of crumpled up shales, and they're very easily eroded, so that just keeps moving things out of the way. Shales break down quite rapidly. And eventually that thing could move a pretty good distance down and away from the escarpment. We talk about that in terms of translation, rotation, and different kinds of vectors and stuff. But what I want to point out here is that which way is up in the rock layers? The shale, the sandstone, and the limestone. We know that stratigraphic up is the way the red arrow is pointing, up towards the top of the diagram. But what about once it finally slumps? It's pointing at a different angle. These block layers got rotated and are kind of dipping. So here's some real examples out there. Here's the real escarpment. Stratigraphic up is to the top. And this block slowly slid down from the escarpment to the right of the picture. You can't see it. And so there's your Fort Hays. Codell's down here at the bottom, and this is Blue Hill Shale. So this thing kind of rotated clockwise downward away from it. This one on the bottom is just like the cartoon over here. That here's our Fort Hays limestone, here's the Codell sandstone, and way over here is the Blue Hill Shale. This thing rotated counterclockwise, downward quite a bit. So all the slumps out there are in different kind of orientations. So again, remember that curvature in terms of what slumps mean. Now, landslide in this picture, I'm just going to show you some pictures. They kind of slide down a more planar surface. There's probably some curved surfaces in there, but they're exposing some of the more planar parts where these large chunks simply move down, and here it's covered a highway. Someone actually caught a landslide occurring. You can see the whole cloud of material moving down that valley, eventually going to make it to the bottom. All right? This is kind of after, and this is during. Kind of unique to, it's hard to, you're not always around when these things happen, and you certainly don't want to be if they're pretty dynamic. Out in California, a major study went on, this subdivision they built in this area. Came out here, beautiful coastline, nice spot to live. And here's on the bottom, it's kind of a cross-section of the geology, and all the layers are doing what? Gently dipping right towards the ocean. So it wouldn't take much to get in here and get some fractures and have some movement. If it breaks away and you get water in there, water can add as a lubricant or weight, and this whole little thing just slowly starts sliding towards the sea. And it has happened. All the streets are buckled, the housing foundations are messed up. One of the things they thought that helped with causing this to move on a little faster was the excess yard irrigation. Everybody wanted to have a nice green grassy yard. So they'd water and they'd water and they'd water. And what does that do? It adds weight, acts as a lubricant, helped to kind of erode physically or chemically, and eventually all it took was a good old California earthquake or two and get it to slip and slide and vibrate and head towards the ocean. If you ever get out to this part of California, check it out. You see this a lot along coastlines that are prone to this. Here's an example from your text again of another spot in Wyoming, 1958, where you had a rather unstable, steep slope, and because of the type of rock that was on top of another one, this kind of more sponge-like rock of the sandstone sucked up and absorbed a lot of water, so it was getting overweight and over, steep and unstable to begin with. And all it took was a little kind of quake to get it moving and extra water, and just slid right down in and covered up the stream, and a lake formed. And eventually that would eventually flood too and cause this to erode out, move on downstream, have a mud flow. So one thing can lead to another. It doesn't have to be just one big movement. So this is the Gros Ventre region out in Wyoming. Up in Ontario, quick clays, and over kind of, we had extra water added to this area. Remember we talked about liquefaction maybe one time, and I'm going to show you some more pictures of it, is that you can simply take unconsolidated sands or clays, add water and vibrate it. It turns into quicksand or quick clay and slowly slides and slumps. The more water it is, the more aqueous it comes. Up in Ontario, a whole kind of section of this slope broke loose and came into this river system. In that case, so quick clays in Ontario. So let's talk about quick clays, okay? Quick clays and quicksands. You always talk about quicksands in the movies. I think there's a movie coming out here called Hidalgo pretty soon, and they're going to have, I think, one of the horses fall into a quicksand spot. The word we prefer to use to describe this is liquefaction. It's where you have unconsolidated material, usually, sands and clays, can be silt, and as it takes up more and more and more water, all you have to have is some vibration. And that vibration turns it, and it begins to behave like a liquid. It overpressurizes the material underground, and it turns to like jello or jelly and begins to flow like a liquid. On the left-hand side, the lower left, you can see this photograph in between the tracks and around edges here where sand squirted out of the ground under pressure as it was kind of liquefied. Here it came up in somebody's front yard, just oozed out. These aren't really scary dynamic situations with this, per se. Here's one out in California again in some of the orchards out there, some of the croplands. There's a goofy nickname out there for liquefaction. It's kind of a tacky name, but you come across it occasionally, sand boils. Sand boils are simply another way, more of a lay way of saying something about liquefaction where sands and clays are oozing out of the ground due to this kind of liquefaction process. Water. I want to look at water a little bit with the liquefaction and kind of a way to make a material unstable. Now, connate water, connate or connate water is water that's trapped between grains during deposition. Connate water is trapped water. Usually, of course, if it's sediments that occur along a delta front or along a beach and a barrier island, and on the continental shelves where most of our sedimentary rocks are produced, then the water in there is going to be salty or seawater. Now, salty water, I don't know if you've ever been swimming in the ocean, you get out, it's kind of sticky. So, saltier water in the pore space kind of acts as a glue. It's a better type of surface tension thing. But if you can get fresh water as the surface of the earth structures change and have fresh water leak and break into this zone that has the salty water in it, the salty water or the fresh water will dissolve away the salt and begin to make it, more like a quicksand or a quick clay. And that can happen particularly along coastal areas. You have to watch out for that. Or older deposits that are unconsolidated that may contain that kind of salty seawater. So again, water can always play some role in this process. I believe these two drawings on the bottom, the cartoon, are from your textbook again, trying to show the situation of quicksand or quick clay. If it's a silt, I suppose you could call it quick silt. It doesn't matter. Here's some liquefaction and rather large scale and some foundations in places in Japan. You certainly have something to clean up. You've fractured some of the foundations of buildings. Here we are along a pond, and you can see that the fractures are helping liquefy this, and the whole thing begins to simply sink into the ground. So this is a little more damage than some of the others. So liquefaction can be a problem as far as a hazard in certain areas. All right, another example of a type of mass movement that was, again, kind of a landslide that occurred. This is in Vaillant, Italy, and this map from your textbook, let's look at this map a little bit closer. This darker area in the middle represents a main body of water that's right behind a dam. Right where the cursor is, there's a dam here. Another steep dam in this narrow valley. And right below it's a small community of Vaillant. And of course the lake that's backed up behind the dam goes way back into some of these tributaries by these other little communities along the shorelines of this kind of mountainous lake. Well, what was happening during the heavy rains in the 1960s is that this slope, here down the bottom of the page, is a cross-section of that area. On the right-hand side where this big red arrow is where these two arrows are right here. Okay? And there's pretty porous rock. They mentioned there were some sinkholes and other kinds of poorly based stability on the slopes anyway, and it rained and it rained and it rained. What does that do? It adds water, it adds weight. Well, it was enough to push it over the edge, and this huge part of the hillside broke loose. Slid right down into the lake. It didn't, hit the dam, but it slid down into the lake and shoved the wall of water up on the other side of the lake, and of course shoved water up and bounced along and up into these other small communities along the lake further up from the dam. But the biggest wall of water went right over the top of the dam. The dam didn't fail. It was this huge wall of water that went blowing right over the top of the dam and went down and really caused a lot of problems. A lot of people died here in this small little community at below the dam. And they were just waiting for the dam to go, but it didn't. They were quite lucky, and it hadn't gone. So it doesn't have to be the dam. Here's an example kind of a liquefaction, slumping, creep, maybe some seawater sediments that gets dissolved by fresher water, and then an earthquake. In Anchorage in 1964, this whole area just completely just fell apart. And there was a whole nice subdivision out there, and everything was pretty much damaged. The bottom picture here is a cross-section. So it's a combination of a variety of types of mass movement, but again, it's that vibration to kick it in. You notice there's snow here, so there wasn't really a summertime thing with too much extra water. So whatever it is can shove it over the edge. Weathering, too steep a slope, too much water, too much vibration, number of things. Here's an interesting one, a really large type of flow they refer to as a debris flow. A debris flow is very gravel-like, very thick and stiff-like, kind of like a very viscous flow when we talked about viscosity with magmas, that broke loose up here on this mountainside and went a great distance over the Mojave Desert floor, traveled a long distance. Here's the eventual tower front, this big lobate debris flow called the Black Hawk. And sometimes it doesn't always have to have water with it. Just enough air, as this thing in between the spaces, can act as a cushion, and if you get it moving, it can travel great distances. So there's a variety of things that can cause it. So it's happened in the past. Here's another one. Let's just look at this slide. Now let's not write everything down. If you want to, you can look up the specific one on Nevados, the Huascaran region in Peru, where really high snow-capped peaks, volcanoes, and avalanches break loose at times. And so in 1970, there was this big earthquake, okay, a large earthquake, 7.7, that's rather large on the Richter scale, and it triggered this large debris flow that come blowing down the side of this volcanic peak. And it hit some glacier zones. Well, obviously the force of that hits the glacier, hits the ice, picks up more water mass, more ice, and that glacier, even though it was kind of in the way, acting as a little bit of a dam, it helped deflect stuff up in the air, and there's even some airfall material that rained down as it blew up into the atmosphere. So it was a mixed bag of stuff that came out of the air once it hit the glacier and then continued to slide down the hill as a debris flow and created quite a mess. And a lot of people died in this particular event. A mixture of mud flow, debris materials, and ice. Again, triggered by vibration. In Hawaii, people would think, oh, that's a nice, tranquil, easy place to go. Now, on the Big Island of Hawaii, where we know there's volcanic activity, we know that that's going on. This is the Big Island of Hawaii. This is the southeast corner, okay, N for north. And you can see a little smoke coming out of the vent, Pu'u'o'o. I think we even looked at that when we looked at igneous rocks and volcanoes in here. Well, this whole southeastern side of the island has a series of ridges and cliffs, so to speak. And this is where most of the eruption is occurring. And all that lava is coming out and piling up, adding weight and oversteepening. So eventually, big chunks of this are slowly breaking away and moving downhill into the ocean, towards the ocean. These steep slopes in Hawaii are called palis in their language, P-A-L-I-S. And the geologists who've been working in Hawaii looking at these, not only the volcanic activity and monitoring all that, they've been noticing that along the edges, the upslope edges of the cliffs, there's some fractures opening up. Little curved arcuate fractures developing, and there's been movement. Slow movements towards the ocean, slow movements downward. And by mapping the micro-earthquakes, they notice they're on curved surfaces in the subsurface. Well, they decided to take Global Positioning System Units, GPS, and set an array of these things all over the sides of the volcano, but particularly the palis, and say, how fast are they moving? And one of the things they're looking for is to say, are the rates picking up? Because we have geological evidence of ancient submarine landslides that are down here off the coastline of all the Hawaiian Islands, for that matter, where huge segments of these cliffs have broken off in the past. And they have created a wall of water, or a tsunami, that are up to 800 feet to 1,000 feet high, where those waves have bashed into some of the other islands. So that's their concern. Are there going to be some of these great big, landslides of this volcanic rock sliding south and eastward into the Pacific? We'll see. So if they start seeing lots of increase on that, we'll have to keep an eye on it. All right, let's go back to that one topic I mentioned, subsides or subsidence. I want to go through a list of some of the things that can cause subsidence now. Some cause, some subsidence. And I'll point out these pictures in just a bit. So let's go through the title of it, Subsidence Causes. And one of the types of things that can cause subsidence is called hydrocompaction. Hydro implies water, and obviously compaction means to move downward, to compact the material. Let me explain a little bit about hydrocompaction. What happens during construction is we get out there with our bulldozers and all our equipment, we tear up the ground, we fluff it up. And a lot of the minerals and the clays and that stuff are all tilted at different angles. They're not compacted. That's why you see them get out there and try to drive back and forth with heavy equipment, or use tampers and pound it back down. If they don't do a good job in getting that compacted, and they build something on it, and the next time it rains enough, that rain percolates into these fluffed up zones, And they slip and they collapse like a house of cards you might build and hit it. And everything collapses downward. Well, then that structure, a concrete canal, a highway, a building, has no support, and it eventually pulls under the force of gravity and cracks the foundations. That happened in the big, what do they call it, the American Canal, where they take water out of the Colorado River and move it into Southern California. And that costs a lot of money to repair. Now, hydrocompaction is not a big worry per se, but it's still a process that happens and can cause problems. So it's where water is involved. Another way to cause the ground to go downward, vertically, is to remove fluids from between the grains in the subsurface. Pump it out. Pump the water out. Pump the petroleum, crude oil out. Because that water underground is under pressure. It's helping buoy things upward. And all you have to do is remove it, and all of a sudden the grains begin to settle and sink downward. Very, very slowly. Fluid removal. Another way is to dissolve it. Chemical weathering process of solutioning. Dissolve the rock. Now, the best rock to dissolve, of course, would be limestone. But once in a while, you might find a salt layer under there. And I'd like to bring your attention now to these pictures over here. Okay, we're going to look at a variety of this kind of downward dropping of the ground. This is a pond, circular pond along Interstate 70, east of Hays, Kansas, about 15 miles. Here's the interstate on the left, and you can see that the surface of the earth has dropped downward. This is referred to locally as the Crawford Sink, or the I-70 sinkhole. And about 800 to 1,000 feet below the surface of the ground here is a layer of rock called the Hutchinson Salt. And there's lots of oil wells in this region of Kansas. And there was an old well right in the middle here, now the ponds covered it up, where the steel pipe rusted out. And normally you would think if that pipe rusts out, what's going to happen is water in the rock layers below the surface would slowly ooze upward. The water didn't come upward and out the well. Waters in those sandstone layers in the aquifers were pulled down towards the Hutchinson Salt because all of the oil wells around the spot were pumping and pumping and pumping and pulling the pressure towards those wells from that depth. And so the water went down and went right through the salt. What did it do? It dissolved it. So the sinkhole out here has been dropping about 5 to 7 inches a year. We'll look at a little more detail of that with some other pictures in a bit. Another example, the same thing. This is again near Fort Hays State University, northeastern Kansas, about 15 miles north of the campus. And this sinkhole had opened up. This view you see is from an airplane about 500 feet up on the bottom right, called the Chrysler Rink or the sink or the Nielsen sink. That's about a 110-foot wide hole, and it's about 105 feet deep, and it opened up overnight. A pumper, an oil pumper, found it because he'd go back to this area and work on his equipment every day, and it happened overnight. Now, it could have been 5 minutes or an hour, nobody knows. But the sinkhole on the interstate's been going down real slow, 5 to 7 inches a year for 40 years or more. This one opened up overnight. Now, what if that kind of activity had happened on the interstate? Imagine driving along in the middle of the night and there's this big 100-foot deep hole, So it's the potential for that, for this solutioning process. A very, very bizarre way to cause the ground to sink a little bit is called organic shrinkage. We used to drain swamps out. We don't do that anymore because of the wetlands law. We protect our wetlands. But we used to try to drain the swamps out, and of course that organic stuff left in the swamp was not too compacted, and now oxygen could get to it. And that oxygen would break down the hydrocarbons, and the ground would simply sink and crumble. A few examples of some disasters happened when they drained swamps and they put some housing developments in it, and the next year every foundation was broken. They just moved everybody out. But that does not happen, so it's a rare possibility that goes on. Of course, mining, coal mining, underground coal mining, gold mining, anything underground type of mining is going to leave open voids unless they fill them. And I know sometimes the ground above the old mines collapses and sinks downward. And you come home to surprise, surprise. And it's not a lot anymore. Here's that I-70 sink looking at it from a different view. We're looking westward now towards Hays, Kansas. In about a month, April of 2000, they're going to tear this overpass up. And for the second or third time, they're going to build the highway back up to its horizontal level. They're not filling this hole in anymore. They're quitting on that. They gave up. But you're going to see a lot of construction here in the next 3-4 months. And Fort Hays State students may be doing a kind of surveying project and some high-tech, fancy kind of research here, if we get it going, on calculating, measuring this slow future subsidence. It's going to continue to do it. So they're giving us the opportunity to maybe check it out for them and monitor that and create maps. So here's a word up here I may or may not have used, and I'd like you to write it down. Anthropogenic. Again, it means human-induced things because of our oil well activities and poor possible taking care of that well with the casing. Probably led to this. That's what everybody believes. Okay, so an anthropogenic. The I-70 sinkhole is caused by us, an anthropogenic feature. Here's some more pictures about this stuff with similar sinkholes elsewhere in Kansas where the Hutchinson salt. Here's a core of salt beneath Hutchinson. Here's this sinkhole over the railroad tracks just beginning. You can see the track still suspended over that hole. It's slowly going down and down and down. Eventually it went even further and bam, filled in with water. And then they moved the tracks around it. Here's a cross-section picture of a surveying of the I-70 sinkhole way back when. There's a little tiny sinkhole just west of it called the Witt sink, the W-I-T-T sink. So there's lots of places where the ground is moving downward. Let's look at another situation here where we remove fluids. Your text has a bunch of examples of subsiding places. I wouldn't say that Mexico City is a coastal city per se. I know there's some lake material down there, but focus on the two I have blue arrows on. Houston, Texas, and Long Beach, California. Even Galveston, Texas. These cities are involved in oil drilling operations. They have removed a tremendous amount of fluid in the form of oil from those regions over a long, long time. And over that time period, the ground has dropped and dropped and dropped. And why? Because by removing the fluid, you reduce the fluid pressure. And that causes the grains to collapse and settle downward. So Houston is a big oil area. Long Beach is a big area. Along the coastal areas, fluid removal. Not every one of these are related to petroleum. Some are simply water. But it's the fluid removal. Here's some shots of Long Beach. There are many places in Long Beach where we still have wells pumping, like in the top left, that are below sea level. There are restaurants below sea level. There are schools below sea level. They just built up great big berms. Here, this is an earthen berm between the marina and this well. Or maybe they were steel walls or they're concrete walls, whatever we had. Here's some of the old pipes. You can see where they had the oil come out and how they tie into that, these little Christmas tree type things, how much more it's sunk. The ground is sinking downward around the equipment, around the bridges. They have to live with this out there. These kind of nice looking buildings, inside there are oil well drill rigs. They put these buildings up to make them look nice so they're not, ugly. They're more aesthetically pleasing to the people who live in the area. They don't want to see them. But they're still pumping. They're still removing fluid. Here's Houston, Texas in 1935. Some dramatic losses, and it continued to sink and drop over the years. Certainly if you're next, the coastline, sea level is going to rise. You're going to lose land. All right, let's jump to another topic of kind of a downward drop, a subsidence that can develop due to this solutioning of limestone. Not like the salt here in Kansas, but limestone. And I want to introduce you to a term, karst. This is called karst features in this cartoon picture. All these different kind of things. I'll mention a few on here. The word karst originated from scientists studying this kind of landform stuff in Slovenia along the Kurs Plateau, K-R-S, the Kurs Plateau. Thus, coming into our vocabulary, the word karst. And if you look at this picture, here we have all these limestones underground with lots and lots of water. All this blue stuff is big gaping underground holes. We call them caves. Here, if you're going to get in this cave, you've got to have a scuba gear on. If you come up in the caves up in the top left or where it's brown, you can hike around. You can crawl around or hike around. But you're destroying the rock. You're destroying the support below the surface. So the surface begins to cave downward and into it. Or sometimes the streams may flow and disappear into a hole, carrying that water down underground, so you get poor drainage. There may be springs coming out the side, and it's just pockmarked all over the place. And see these little round circular pits. They're called sinkholes. You go to Kentucky or Florida in particular, you'll see lots of this type of terrain called karst topography. These are some of the features. Caves and sinkholes are the main ones to think about. But it's a form of subsidence. Here's one in Alabama, 1972. They called it the December Giant. It appears that it just happened in the middle of like a state forest maybe here, or a federal forest. Here's one in Florida again, Winter Park, 1981. A little bit of water, filling that in. The water table is pretty close to the surface in Florida. Here's the one I showed you earlier. All right. When these begin to develop, you can sit there and watch them sometime. Just watch them slowly crumble and sink into the ground, and things move down, and kind of sad. So if you want to fly over someday, here's the best view. Become an astronaut, get up there, and take a look at Florida from space. And in here we could see, the main part of Florida, the Florida Keys at the bottom. Miami's over here on the right-hand side. And you just begin to see lots of these little darker colored lakes in here, pockmarked lakes. Here's a better view, kind of an infrared photograph. And as those lakes got bigger and bigger and coalesced, you start advancing this development of topography. So Florida has a lot of population. They need a lot of water. There's a lot of homes, a lot of highways, a lot of industry. So they want to know what's going on. And they hire a lot of people, divers in particular, to get down there and figure out the plumbing. Now this particular map that you see on the bottom of the screen, it's kind of like, it's not in Florida, but it's what cavers do, some of them do, to map caves. So we know where the connecting parts are. Where is that water migrating to? And of course you get to see all this spectacular cave stuff. Stalactites and stalagmites and all the beautiful formations in the caves. But it's a very dangerous job. This is an extremely dangerous job getting under there, because the way in which you dive is different than in the ocean. You don't often carry the oxygen tanks on your back. You may have them on your hip when you get into some very tight places. And getting in here can stir up the mud, and you get turned upside down sometimes. And they bring a lot extra tanks along and have specialized ropes and know exactly where they go. And they're always in pairs or large groups as they map this. But here's some of the newer anthropogenic sink, the biggest, fanciest one. I want to have you write down this word in the bottom right, gypstack. South of Tampa, there are some mining operations to get phosphate out of the ground. And some of these phosphate piles, over on the top right-hand part of the picture, are these huge piles of phosphate and gypsum-rich stuff. The mineral gypsum has sulfur in it. And if you mix sulfur with water, you can create an acid. Sulfuric acid is much more acidic in dissolving power than rainwater, carbonic acid. And once in a while, all of a sudden, because that has corroded and eaten so quickly through the limestone below the surface, huge sinkholes form just instantly. And here you can see it. This is a news chopper. See where that arrow's pointing? That's a helicopter. Quickly flying over this hole to check out, equipment will fall in sometimes, or they'll lose their stuff. So sometimes they really have to monitor and watch this. They have a team of people looking at these things. Okay, here's a type of subsidence you may not have thought about. Subsidence associated with deltas. Here's a nice, beautiful shot from space of the Nile Delta. The blue waters of the Mediterranean up here, okay? And here's all the vegetation on the delta. The rest of this is desert. A lot of food production along that river system. As the river floods, it keeps bringing in more and more and more sediment. That's what deltas do, all right, as they move towards the ocean. And that sediment compacts and gets buried and moves downward under natural subsidence, weight burial. Just the natural weight causes it to subside. Well, what if you did something to the river. What could happen? Let's take a look at the Mississippi River. All right? Here's the main channel of the Mississippi today. Here's the kind of the bird's foot part of it, bringing sediment into the ocean. And you can see the sediment plumes being moved into the Gulf of Mexico. All right? We live along that river. Big cities are along that river. A lot of agriculture along it. A lot of places now down this area are actually below the level of the river because the land out here is subsiding. It's sinking downward. And the reason why it's sinking downward is we'll get to in the next slide. I want you to think about that. Something's going on with what we did on the river. Kind of a map of subsidence, kind of a contour map that your textbook has. I don't think I'll go into it too much with this, but here's another diagram. And there are certain zones along the Mississippi Delta that are in trouble. There's saltwater encroaching on these lands and killing off the vegetation. And we're losing acreage every year because of it. Now, why is there subsidence? Let's think about it. We have channelized the river to speed and get the water past our community downstream. And what does it do? It takes the water plus the sediment as quickly as possible and dumps it out here in the Gulf of Mexico. Or maybe way back up the river we have a bunch of locks. And by damming it up, we put the deposition there. So the amount of deposition going onto the floodplain has gone down. We've reduced it by our activity. And so what's happening is that natural subsidence is still going on. So it's going to be interesting to see what happens in the next 50 years or 100 years as this process continues. All right, I told you I'd tell you about a special weird case of creep. Okay? Remember, creep is a slow downhill movement of the surface of the earth. And a very specialized case of that we've referred to as creep is called solifluction. And here's a picture of a hillside north of the Arctic Circle where we have lots of permanently frozen ground, thus this term permafrost. In the summertime, when you have a lot of sunlight, the upper foot, 2 foot, depends on how much the energy penetrates, thaws that permafrost out. And this turns into liquidy slush and slowly slides and drapes down the hillside. Solifluction, remember, could only take place in the Arctic. I could ask you a question in that fashion. That solifluction takes place in Kansas. No, it only takes place in the polar regions where you have permafrost. Here's a kind of a quarry outside of Fairbanks, Alaska. And of course you have frozen ground, but if you look at this area here, that permanently frozen ground penetrates pretty far into the ground. Really can destroy it. Here's some of the old homes early on before we knew what to do and how to deal with solifluction. A lot of damage to the foundations. Not only is it the freezing sometimes and the thawing that can take effect. Here we are on the, above the Arctic Circle in the Brook Range, on almost to Prudhoe Bay in the Arctic Ocean, and here's this kind of wild tundra, and this white stuff in here is referred to as needle ice. Let me go back to that shot. Sorry, I'm going too far ahead here. This needle ice, all right? These are long blades of ice crystals that develop, and they call it needle because it's like a long sewing needle in this case, and it expands, and it causes the ground to get really bumpy and hummocky. So as it gets cold, it expands and shoves upward. As it warms up, it melts, and everything sinks down. So seasonally, there's a lot of changes going on with this type of solifluction and needle ice development. And when we put things in like the oil pipeline in Alaska and have this haul road alongside, we better make sure we've protected this area from earthquakes, from the thawing out of permanently frozen ground. So here's a close-up of our pipeline. The water, the crude oil going through that pipe is hot. You got to keep it hot, or it stiffens up. And so you got that very central core of hot oil. There's a huge thick wrapper of insulation around that, and then this aluminum on the outside of that with straps holding together that sits on a 4-pedestal base that sits on a movable kind of steel railroad track system that can slide back and forth. So any heat that comes out of that oil might make it all the way through down to here, might make it into this, might make it into this, and this is a hollow tube. And then they build these fins, like on motorcycles. You look at the top of an engine motorcycle, got those fins to cool it, to keep the heat off. So at Fairbanks, you can go and get a degree in studying how to build all kinds of different fin systems for whatever, for permafrost and solifluction. Keep it cool, in other words. You don't want this ground thawing out. If you do, this structure is going to collapse, and then we worry about, that breaking. And for earthquakes, by the way, these are big little, these are kind of rubber shock cushions. This thing can slide back and forth. Lots of ways to protect that thing. So geologists look at all these different kinds of mass movement. All right, we want to know what kind of rock types are involved in our country. So here we have a geologic map of the United States. And so these colors represent different types of rocks of different ages and different styles, different amounts of fracturing and weathering. And so we study that, and from that we make maps that are called landslide or mass movement potential maps. Where are the worst places to be for mass movement? Well, you can see here in the Appalachian Mountains a lot of problems that are related to nature as well as to anthropogenic things, like the mining operations. Here in Kansas, most of this little stuff here, this green thing, that's due to creep, a little bit of subsidence. But finally get along the west coast in California, or in the mountain systems again, that's where you have the biggest potential. So again about this, watch out for things. So we want to fix them. Let's talk about a few things to fix things up, and we'll get close to wrapping up our class today, all right? So mitigation is how we prevent stuff. What are some things we can do to stabilize slopes? As you drive along, you might see some of these things. For example, in the top left, we have like rock bolts. We'll drill a big hole into the rock through the layers and set a huge kind of screw or pin into that and put a big bolt on it. You can see the close-up of these rock bolts now. Sometimes we may put wire nets, real thick, heavy steel mesh nets across the rock surface. If something breaks loose and starts falling towards the highway, it's not going to hit your car. Or if you're down here at the bottom of the slope. So rock bolts and wire nets are types of kind of mitigation techniques. Here's kind of a cartoon of showing how we kind of secure those layers on this more unstable slope from sliding down into the highway. Here's where we might say, well, we've got a highway we built through here. We cut this slope, it's real steep, and this has become kind of unstable. That's the potential to move. Well, let's tear it off. Just get rid of it. Through construction, remove it. Now, whether you can do it or not depends on what? How much money you have. Is this a community effort? Is it a county effort? A state effort? Or a federal effort? And all kinds of monies are tied to how much and how well we can mitigate the areas around us to work on stuff. This is kind of hard to see, and it might be hard to see at home. I'm not sure. But on the right half of this picture, you can see what appears to be little tiny white dots all over the place. Those are little large-scale nails, and attached to it is a net, a protective net. On the left-hand side over here, this is the non-net side. It kind of edges about right here. And this individual is crawling all over this whole hillside with a special hammer, pounding in these things to hold that net in. So it just depends on what kind of things we want to do. Here's a shot looking down on a kind of little cul-de-sac in California. This house, there's either a road down here, and you can see where they move up into their house. Well, to protect that, by this steep slope, they'll vegetate it. They'll put water drains in to keep the water out of the slope. And in this case, they've terraced it. Notice that this part of the slope, the vegetation hasn't taken hold yet. So whatever it takes, again, in one region to the other, to stabilize your slopes. Rock bolts, nets, terracing, water drains, vegetation. More and more possibilities to take care of it. Here's a wild one, shotcrete. Remember that. You can spray it, kind of a liquid concrete called shotcrete. And here they're spraying it against a steel rebar kind of arrangement. Sometimes they just spray it right on the slope itself. I've seen this in many different stages where it's broken down. This, what appears to be a kind of a board formation and maybe the rebar and then the concrete, that's pretty strong. That's pretty expensive to do, too. So here's some more. Retaining walls, tunnels, rock sheds over highways to let the slides come down and go right over, whether it's a snow shed or a rock sled. Retaining walls of different styles. The one on the lower left has a really wild name, gabions. G-A-M-B-I-O-N-S, gabions. They're like cubes of rock put in like chicken wire. It's not really that thin. And then they simply pile up the cubes and try to get a little bit of natural slope to it, because it's much harder, more resistant than the natural material. So there's just hundreds of ways in which we try to conjure up ways to fix things. What about making the grains underground stick better? Some kind of special gluing or cement. Well, there's a whole category of things that we lump under what we call grout. A lot of times people will grout along the foundation of a house. They inject this material underground. There's a very specialized injector systems here of different styles, and they inject that stuff and it really cements and hardens it, gives it more stability. So yes, there's lots of possible things that we do, and everyone's out there trying to protect us from this mass movement kind of stuff. So I believe that's it for today, and we'll see you next time.